basically have like a platform that we try to deliver personalized experience and content to end user on devices based on the context that they're in. A very like simple use case example could be, for example, one of our biggest customers, like TV, can come to platform and define a rule, say if the user has walked for more than 2 kilometers for
usually we spend the whole night on one paper, but tonight we're going to go very broad on many papers. So we have about 10 people who are going to come up and propose one paper. They'll have 5 minutes each, and I will use a timer so it doesn't go long. And the idea is, yeah, they'll just explain, make a pitch for the paper, explain what it is, get into very briefly the details without going too deep. And then at the end, we'll all vote on which papers we would like to see presented in depth at ACE. So we've got a break halfway through, and otherwise I think we can get going. So, oh great. So, Yivi? So hold on, are you ready? Are you guys ready? Sorry.
Yeah, we're already live.
Already live, okay, great.
So you guys have to, can you also say that there is a camera? Okay, I'm saying it. So there is a camera that is showing folks that are sitting on that side. If you don't want to be shown, come sit on this side. Or if you want to be famous, go sit on that side. Your choice.
And I'll just put my hand up when there's 1 minute left.
Okay.
So you know.
And please just stand on the other side when you're speaking, since the microphone is over there. So go there.
So,
Think over.
yeah. So where should I stay here?
Yeah, just on this side is great.
Okay, so start.
Yeah, go ahead.
Okay, so hi everyone, my name is Juri, and today I will present you an abstract about Cobra model. So besides it's a very fancy model, Cobra, which almost sounds like a gang name. It's a very sexy new approach developed by data scientists in Google DeepMind. And I would like to show you or explain why this paper or this approach needs more attention. So first of all, my motivation why I speak about this is that I recently became a research associate with ACE, doing deep learning based recommender systems. And what we aim to do is we want to build some state-of-the-art model and incorporate some deep learning, reinforcement learning model. So there are two main issues in reinforcement learning, and first of all would be data efficiency, and the other issue would be task-relevant perturbations, and this is what this paper tries to solve. So what it is? The model basically incorporates two branches. Imagine that like a household, and in the first floor of the household, there is a framework which performs exploration tasks, and in the second floor of the household, there is a floor which performs task-specific operations, and these models basically is first of its kind in the industry, because what it does, it's combine unsupervised learning for object-oriented algorithm, curious driven exploration, and model-based reinforcement learning. And this is where the name of the model comes from, Cobra, because it's curious object-based search engine. And now let me explain the model a little bit. So first of all, there is an exploration task which learns about the objects and dynamics of the environment, but it's not rewarded. Unlike in other reinforcement learning models where rewards happen, this exploration is only there to learn about the objects and the environment. And then it moves to task phase when the model uses what it has learned to actually perform individual tasks. In the exploration framework, there is architecture, and let me tell you, this whole household consists of vision model, which is basically the input model. You put some pictures into this vision model. Then there is transition model, which cooperates with exploration policies. So it is also called adversarial learning, because if you imagine a picture where you have an object and you want this object to move, but this model, the exploration phase, needs to learn where the object is. So, but the object only only contains, let's say, 1% of the picture. So it's actually more efficient to apply some adversarial autoencoder, which then tries to find actually the space where the objects are not, and then based on the highest loss, it actually communicates with the exploration policies and learn about the environment. Once this all is done, the model switches the exploration mode and goes to task phase, where the Cobra tries to estimate reward functions, which is also different from other reinforcement learning models, because here here in Cobra there is no policy network. So in the end, I would like to emphasize and summarize that this model developed by Google DeepMind is first of its kind, incorporating a lot of reinforcement learning, curiosity exploration models, and it will certainly be discussed and explored more in research areas and industry. So thank you for your attention.
That's me. Okay, guys. Hi, everyone. Okay, so this is the paper from OpenAI team. And OpenAI team was working on the reinforcement learning system that was implementing hide and seek games. So they had two groups of agents. One group of agents were hiders, another group of agents were seekers. So there were random objects that were movable and non-movable objects. And so what they found is that, and why the paper called autocurricular, is because the tasks were really created by one group of agents for another group of agents. So when the hiders were creating the room and were using the blocks to block the entrances into that shelter, right? So then they were creating defactors. So they were creating a task for the seekers to find a way to still get into that room. So using the blocks, and so what they found is that it's pretty much very close to how human teams were working. So they saw agents communicating, they saw them cooperating. So they saw them working in teams, actually building those shelters and moving the blocks in teams, dividing the tasks among themselves. So Pretty fascinating findings. So they found that they were working through 6 phases. They started with just randomly running around that space to the point where they were copyrighting. So it is reinforcement learning. They build it, let me see, because I didn't memorize the entire infrastructure. So they build it using two separate networks with different parameters. Policy network, which produced action distribution, and critic network, which predicts the discounted future returns. So they used RAPID, which is large-scale distributed reinforcement learning framework, which is the OpenAI framework. And so it was decentralized execution and centralized training. So anyway, it's pretty interesting. So it's probably I think it's the first work like that was done with where there were multiple teams of agents working together. So the code is actually on GitHub. So I didn't have time to look into the code, but the code is on the GitHub. If you decide to use that paper to one of the bigger sessions, so we probably can dive into the code. Also in the paper, if you look at it, so there is a link to the blog post where you can see the videos of those agents, how they are learning, and all the 6 stages that they are describing in the paper. Okay, so very interesting, very fascinating. It was very interesting for me to read this paper, even though I'm not a reinforcement learning specialist.
Yes.
So I started only a couple months ago looking into reinforcement learning. Okay.
Thank you.
Thank you.
Oh, sorry, that's I think you, Michael.
Oh, why is it L?
Yeah, you wanted to test these. That's what
Just here, right?
Yeah.
Okay, hello everyone, I'm Michael E. Y-E, not L-E, not Michael E. But okay, anyways. So let me put this pencil away. Okay. So when you think of like neural networks, like optimizing neural networks, like it often also implies, some sort of training algorithm, like gradient descent. However, this paper completely changes like the way you think about optimization. So instead of optimizing for like weights and like parameters of a neural network, it optimizes for like the architecture or the hyperparameters, right? And you may think this is just like any other AutoML paper, but it's actually different because in AutoML, or automatic machine learning, when you evaluate a neural network, you still have like a training process, right? With this, they literally it's called weight agnostic neural networks, which means there's absolutely like no training at all. And it turns out these neural networks can actually perform really well on tasks. Just an example, which I'll go in depth later. For example, one of these neural networks that was never trained had the same accuracy as a traditional neural network on the minced digits data set, which is like crazy to me. But anyways, okay. So before I get into like how they did this, I want to talk about the biological inspiration of this because I find it super cool. So when you think of training, the analogy is always like learning, right? So with this, you can think about it as like using machine learning tactics to design a brain that has intrinsic advantages over people. And you see this in like ducks. They know how to swim, or tell me if I'm wrong about this, but like they know, they have these abilities before their like parents told them anything, right? And in fact, with ResNet and like some image classification convolutional networks, if you just initialize the weights randomly compared to a regular neural network, it actually does better in computer vision, which is like, what? But anyways, now how did they do this? So it's actually really simple. They use a genetic algorithm, which they call it like neuroevolution, it's called NEST. But anyways, so it's just a 3-step process. Generating the initial population, and then evaluating like the fitness, and then the reproduction phase, right? So they didn't talk about like exactly how many neural networks they started with. so I'm not too sure about like the initial population size. However, for the second phase, for evaluating fitness, something I found interesting is they not only take into account like the accuracy of the model, they also take into account the complexity. So that means to justify any increase in complexity, you have to make your model more accurate. And how they evaluate like the no training thing is they put a shared weight across all the weights. So like every single weight is 2, right? And they actually pick a range of weights. So they test the neural networks on like -2 as a shared weight. They test on like -1, and then like 0, and then 1 and 2, right? So that's how they had that like weight agnostic element in the evaluation phase. Now finally, for the reproduction, they just picked, like, it's really just like a genetic algorithm. So you just pick the best performing neural network, and then you the operations you can put on it, like the mutations, can be adding an extra connection, adding an extra node, or changing the activation function, which actually the activation function could be like just ReLU, or it could be like sine cosine, which is super cool. Okay, now why is this important, right? So the first thing is explainable neural networks, because that they can have all these different activation functions. Like one of the examples is like a bipedal walker, but I'll just, since we don't have enough time to like explain everything, I'll just do like a really simple example. For example, you have a neural network that wants to like draw a circle, like wants to replicate like a parametric function, right? Chances are when you use this, you'll find a neural network that has like sine and cosine as the activation function. Okay, so that's pretty cool with explainable neural networks. Yeah. And then next, in automatic machine learning. So usually when you think about it, they always train the networks, which takes like a lot of computational power, right? So with this, because the results are actually like fascinating, where they can have a weight agnostic neural network that can perform as good as a regular neural network on the MINS data set. Think about that implications in automatic machine learning, right? So yeah, if I do get more time on this, I would love to like investigate into the application and like code something up. If you guys have any ideas, come find me after. But yeah, thank you.
Hi. Hi. So my name is Susan. There's 2 papers that I'm going to be talking about today. They're both by Google Research. And they're both on recommender systems. So I'm going to kind of treat them almost as one paper. So first of all, I'm just going to go through the problems that they're dealing with. So it just so happens this one is first. So what the setup is that when they're evaluating recommender systems, they say that a lot of thought and a lot of research has gone into like making the points accuracy more accurate. So what this means is that when you have sometimes like collaborative filtering or like sort of like what's that called, recommender system algorithm, they often have like points, right? Like let's say it could, like if you normalize it from 0 to 1, like maybe for this video, like maybe the algorithm outputs like 0.4, and therefore that should be better than one that's like 0.3. So that's like what they're saying, that there is a lot of research that's going into making these points more accurate, but then the reality is that often, like when I'm doing recommender systems, like the way I display it is really just by ranking, right? Like maybe the points could be very accurate, but in the end, it's mostly the ranking that affects what is displayed to the users, like say on YouTube, which is what they did a lot of testing on. So I feel like every time I go to YouTube now, it's gonna end up on one of these papers. But so that's what they're saying. They want to focus more like on a rank-wise like recommendation ranking. And then for this paper, I'm just gonna give more like a broader, like high-level overview, because they do go through a lot of like statistical and like mathematical proofs. But basically what they're saying is that there's gonna be the scores, the points, but then if you just like swap the ranking, so let's say there's 5 videos, and then for a video that you click through, right? Like usually a problem that they face is just if you recommend something that's higher, it'll just be clicked through more often, regardless of whether it really is ranked better, or even if the points is lower, but you just put the rank like higher, then it'll automatically be clicked through more often. So like judging from, they want to base the accuracy kind of like how much time you spent on it after you click through. So given a click through and with the same engagement, is the expected ranking the same? So if that's the same, then they consider it a more fair evaluation. So one way to think about it is like, if these two videos, like I've both clicked through them and watched 1 minute of them, like is the expected ranking, like should this video be ranked like 2 or 3 for me? Like they should be the same given the algorithm. So both of them should be output like maybe rank 2 or like rank 3. So that is like the high level view of this paper. So the way I kind of seeing me using it is like it's true that sometimes the points might, like it's good to be making them more accurate, but in the end the ranking is what is causing like the real kind of effect to the user. So I think that's pretty useful for me. So I'll go to the second one. So this is also by Google, and then they ran tests on this one on YouTube. So this one is recommending what video to watch next. So this is more on so the previous one was more like on a evaluation kind of, or like accuracy type of kind of research. And then this one is more like on the network architecture. So they propose multitask ranking. So I think I see here large scale multi-objective ranking. So basically what this one is, they're training on the, instead of just on, okay, let me gather my thoughts here. Yeah, so, okay, so there's like a multi-expert, a mixture of experts. So in kind of like neural networks, this means that for, let's say it's an image recognition, there might be an expert that is more for detecting like what this image is, and then maybe one expert for detecting like what pose I'm in. So not like one full network that detects like both like who I am and also like what pose I'm in, but rather like one for each separate thing. So that is the mixture of experts architecture. So like apart from that, there's also a multi-gate architecture which detects which expert to use. So like let's say they think that for the pose expert, that maybe like this portion is more important for the pose. So like maybe like the way my legs are, or like maybe like the way my arms are. So like the gates will kind of determine like how the expert is applied, basically, like which way is better to apply the expert network. So I'm using kind of like a image example here, but I hope it translates over into the recommender system, which I feel like I wanted to come up with an example, but didn't happen to have the time. But basically that is what they propose, and they want to, the problem that these two papers are kind of fixing is just like kind of the biases that like the ranking might have, as well as kind of what is the recommendation system focusing on? Like, is it focusing on the right thing for the right kind of like small detail of the user's behavior? Yeah, so that is the outline of these two papers. I find them personally useful. Maybe some people might be, might find it useful as well. So, thanks.
All right, yeah, so we'll take a quick 5-minute break. Feel free to get some food and chat, and we'll get started after that. You ready? Okay. So, all right. So we're about to get started with the next set of papers. Before we do, I just want to mention this link really quickly. So members.ai.science. If you log on here, you can have access to a whole portal for ACE members, and this is where you can view your workshops, discount codes you have available, sign up for events, and everything like that. So even if you're already in Slack and getting the emails and whatnot, please check out members.ai.science and sign up there. Anything? Oh, sorry, member.ai. Xiang's Xiang's literally updating it right now. Okay.
And we're barely joking.
But if you go to ACE website, on the top there's a link.
Yeah, there's many options to get to the link, but please go
To
there.
the level that it is confusing.
So,
Max. Okay, so the paper is about sparse convolutional neural networks. The main contribution is that the network they built is noise resilient. So the way they tested it, I'll get into the details later, is that they tested an MNIST data set and then put up to 50% of basically random bits in there, and the network performance just declines a little bit. And they compare it to a more traditional CNNs, and then basically that error drops dramatically. So how do they do it? So they introduced this idea of sparse neurons and basically sparse neuron, and they make sure that each neuron weight, basically vector, can only accept a certain number of non-zero inputs, and everything else should be basically zero. And let's say you have a neuron who accepts 1,000 connections, and for that neuron, the weights are going to be all zeros except for 100. And so in order for this neuron to get activated, the incoming activation should be active precisely at those locations where the weights are non-zero, and any other places the activations have no effect. So that's the main component of resiliency. So how do they do it? Is basically they initialize the weight matrix for fully connected multiplication with a certain like sparsity level. So basically, let's say 90% are going to be zeros, and only 10% of all of the activations, all of the weights in a weight matrix are going to be non-zero. So that's initialized from the beginning. And during training, that setup is not changed. Okay, and another thing is that they after this layer has been applied, this like matrix multiplication, they replace ReLUs with top K activations. So basically, they don't use ReLUs at all. So the nonlinearity they use is after matrix multiplication was applied to activations, they only select top K, like let's say 20 or 50 activations, and everything else is getting discarded. And since every time you process like a batch of data, those top K activations are going to be at different places, it introduces nonlinearity in this way without actually applying any direct functional nonlinearity. So that's for the fully connected layers. Then they do it for.
I know I'm not supposed to, but activation functions usually include some nonlinearities, right?
Yeah, they don't use
by
it.
Activation, you probably mean just the linear side of the.
Yeah, exactly.
Okay.
So they don't use any specific activation functions. They basically do matrix multiplication by like incoming activations by the matrix of weights, and then out of those activations they select top K.
Okay, just because you call it activation is confusing. Let's just call them like the nonlinear, because that's just weights times whatever value.
Yeah. So basically, weights times the incoming
inputs,
signals.
right?
Yeah,
The
inputs.
input signal.
Yeah, let's call it inputs. Yeah, and then to make sure that all the same top K neurons don't stay the same, they introduce an algorithm that keeps tracks of which ones get activated more frequently, and basically make sure that those get basically after a while they get like dormant, whatever. And for convolutional convolutional layer, they keep convolutions the same. They only remove ReLUs and also apply this top K activations.
And so that's what they do, and then they compare it to more traditional CNNs. And for that purpose, they test it on MNIST dataset and also Google speech dataset. They train like dense networks and sparse networks containing 2 convolutional layers followed by like a fully connected layer and then followed by a softmax. And then they compare. So basically, initially when they train them, they all have similar performance that is pretty close to state of the art. Like for MNIST is 98, 99%. And then basically this proves their point that actually sparse networks can have more efficient sparse representations compared to dense networks. Like they have fewer parameters, yet they are able to learn to the same level of performance. And then they start degrading the inputs by introducing random noise in the images and also in the spectrograms. And they record how performance degrades over time. And what they find is that for dense networks, performance drops significantly after 10% noise. And it drops up to below 40, like it drops from 99% accuracy to below 40% accuracy. And for sparse networks, the performance goes from 99% to 85% around when you have 50% of random input. Yeah, and also they have some theoretical derivations and explaining what's the probability of like of matching of random vectors. And another thing is that when GPUs get more efficient at processing sparse matrices, you can actually achieve those high accuracies with much smaller computational costs, but it's not there yet. But that's another benefit up in the future. Yeah, so that's I guess that's it. Yeah, thank you.
Hello everyone. Yeah, this is a paper that is fresh out of the archive oven. It will be presented at the MNLP 2019 conference this November. This paper deals with the task of style transfer for text. For those who are not acquainted with this task, style transfer for text basically boils down to answering the question, can you reliably separate the content of the text from the style in which it is written? Now, an example of this task would be, can you convert a sentence written in informal English to a sentence in formal English? A more complicated version of this task would be, can you convert a sarcastic sentence to a non-sarcastic one? Well, the latter would make my life a lot easier because I'm sarcasm oblivious, but one can dream. In reality, this task is incredibly difficult due to lack of and difficulty in annotating data, and the very subtle ways in which style and content are intertwined in text, the discrete nature of text, and also the lack of robustness in automated evaluation measures. So how does one even evaluate this task? There are 3 dimensions along which the task is usually evaluated. One is fluency and coherence of the text, one is content preservation, and one is transfer strength. Now there is tension between the content preservation and the transfer strength because there is a trade-off. If you just copy the source to the sentence to the target, you have 100% content preservation but 0% style transfer. Likewise, if you make aggressive changes, you are likely to have good style transfer, but you lose all your content. So this paper tries to induce a win-win in both those dimensions by leveraging the power of out-of-domain data. Now, this field got a boost starting from 2016 when the first supervised methods with parallel data came into play. They borrowed techniques from the machine translation community and adapted it to this task. Later on, people got excited about unsupervised methods that tried to disentangle the content and the style in the latent space using variational autoencoders, adversarial learning, etc. But they are very hard to train and require lots of data. This paper tries to deal with the data bottleneck by trying using out-of-domain data. So the paper uses terminology source domain and target domain. I'll just describe that to avoid any confusion. The source domain refers to the domain where you have a lot of data and that is not related to the domain that you're working on. The target domain is the domain that you're working on. And in this paper, they have two experiments. One is sentiment reversal and one is formality. So for example, for sentiment reversal, the source domain is IMDb reviews and the target domain is Yelp reviews, and you're trying to negate the sentiment. That is your task. So this paper proposes two models. One in the case where style information is known for the source domain, for the large amount of source domain data that I have. One where style information is not known or it belongs to some other styles that is not related to the task at hand. So okay, so consider a style transfer model which has two components of the loss function. So, I'm already need to be dragged out. Okay, let me, okay, I'll try to be as concise as possible. So, there is a autoencoder that is trained with both the source and target domain data so that you are able to preserve the content better. And to preserve the, so that you don't end up with sentences like the pizza is dramatic. You use domain-specific style classifiers so that the source, the characteristics of the source data are not imbibed in the target sentence that you are generating. So yeah, that is the gist of the model. I'm sorry I couldn't get too much into detail into that. Why is it exciting? Because this is a domain adaptation, everyone. It's awesome. I hope that's my pitch, and I would, yeah.
What do you think is?
Okay, can I take 15 seconds?
Yeah.
Well, you have another 5 now.
Mm-hmm. Is this the last paper?
Of the night? No.
Oh, okay.
Good try, though.
Okay. Yeah, so this paper is about using the information bottleneck principle for unsupervised extractive text summarization and self-supervised abstractive text summarization. So what does the information bottleneck principle say? Take a input X and then you squeeze it through a bottleneck so that you produce a compressed representation, which can be such that that compressed representation can predict an external variable Y. So contrast this with an autoencoder. An autoencoder does a similar thing. It compresses the input, but here it's focused on the compression is done in such a way that you can reconstruct the original input. But in the case of summarization, what do we need? We need to discard the details and the minutiae and preserve the relevant information. And there's nothing in the original formulation of the autoencoder that prevents unnecessary information from being in the compressed representation. State-of-the-art autoencoder methods that use for text summarization actually try to solve this problem by using, by augmenting the loss function with other terms like topic loss, language modeling loss, length penalty, etc. But the authors of this paper, they argue that the information bottleneck principle provides a much better, more elegant way of looking at the problem and easier to train and etc. So okay, the information bottleneck principle uses a inductive bias, which is inductive bias of linguistic cohesion. Linguistic cohesion is the assumption that if a topic is being spoken about in a particular sentence, the preceding and succeeding sentences are also speaking about the same topic. Now, using this inductive bias, they adapt the information bottleneck principle to text summarization. And now I can phrase the text summarization as this. Take an input X, take a sentence X, squeeze it through a bottleneck to produce a summary so that it can predict the next sentence. That is due to the linguistic cohesion property where sentences are broadly speaking about the same topic. So the formulation of the information bottleneck objective function is as follows. It consists of two terms, the pruning term and the relevance term. The pruning term tries to minimize the mutual information between the source, and the input, and the summary, and the relevance term tries to maximize the information, mutual information between the summary and the next sentence. Using this, you can formulate a conditional language modeling objective where the language modeling language model is conditioned on the summary. For this, they use the OpenAI GPT-2, the 117M model. So in practice, they do it using an iterative algorithm that deletes that searches for successively shorter subsequences of the input and deletes the unwanted ones during the pruning step in the model. So that is extractive summarization. Then you have abstractive summarization. So abstractive summarization takes place so now you have an extractive summarizer. You take all your input documents and you run your extractive summarizer through them. Then you have a sentence, and in the extracted summary, you join them together with the TLDR as a delimiter. And then you fine-tune your language model on all the sentences. And there you get your abstractive summarization. And why is this interesting? I think they provide a very compelling case and to view summarization through this particular principle. And I think it's a very promising avenue of research ahead. Admittedly, they are not I think state of the art. They are competitive, but I think if this is a place where more research needs to be done, yeah, I think that's what.
Hi, my name is Harish. So this I think Suhas made my job a bit easier by talking about what extractive and abstractive summaries is. The gist of the paper is that it's a model that does abstractive summary of long text documents. This is a fairly new paper, and so am I new to the topic. So basically, to summarize, they generally use sequence-to-sequence or encoder-decoder models. And coupled with attention mechanisms, the accuracy of the model improves. But the problem is those models are parameterized on RNNs, and RNNs by itself has the problem of scaling up. So the authors, they present an approach where they use the sequence-to-sequence model to generate an extractive summary of documents. That's the first part of the model. And using that first part of the model again has two subparts, which I'll talk later. And in the second part, they use a transformative language model, which they condition using the extractive summary that they generated using the first model. So so in the very first model, which is using sequence-to-sequence decoder-encoder method to create an extractive summary. They have two models, in which in one model they use something called a sequence-to-sequence sentence pointer, and in the second model they use a sentence classifier. So the sequence-to-sequence sentence pointer is just a second. So yeah, it's based on the pointer networks. It's based on pointer networks, and then once the transformer model is being conditioned using the output from both the extractive models, so they have three possibilities. One is using just the extracted output from the pointer networks, and then conditioning it on the transformer language model. The second approach is to use the extractive summary generated from the sentence classifier and use it and condition that onto the transformer language model. And third is using a mix of both onto the transformer-based language models. So as per the author, doing this kind of improves the accuracy for not only the overall abstractive summary, but also the extractor summarization accuracy also increases to a greater extent. So even for an example, the abstract itself is machine generated. It's not written by author for this particular paper. And towards the end, they also present few qualitative results wherein they generate machine abstracts generated by these models, and the abstracts initially written by the authors. And then if you actually look into both of them, it's pretty cool. So my pitch why this paper should be taken is, first of all, it kind of makes our life easier, not having to read through the entire paper. Second thing is, it itself by default talks about 3 different models. So by investigating further, you get to understand how 3 different models work. Thank you.
Hi everyone, my name is Elham. Sorry, my laptop just maybe. Okay. Hi everyone. So I was hoping that I can start with a joke, but I couldn't think of any, so please laugh for Thank you.
So fun.
Yeah.
That was a really good joke.
Okay, so, and I also forgot to print the paper, hoping that I'm doing, something for the environment. So I'm going to be talking about this paper, which is about, so the idea is, can we use language models as a knowledge base? And so for a long time, knowledge bases have been used for storing complex structured or unstructured information. And we can run queries to retrieve information from knowledge bases. On the other hand, recently, many interesting language models have been trained, including BERT and ELMO. And these language models have been trained to be able to predict the next word in a sentence or a single token in a sentence. And we know that these language models contain vast amount of linguistic information as well as factual information, relational information. So a natural question that comes to mind is that can I use a language model as a knowledge base? Okay, so that's the idea behind this paper. And the motivation is that to develop a knowledge base, we need to do a lot of work. So a very complex pipeline is required, schema engineering, human supervision, and the pipeline is prone to error. So if a small error occurs somewhere in the pipeline, it can easily propagate. On the other hand, language models we don't need human supervision for training a language model. We don't need schema engineering. the practitioner who wants to retrieve information has a lot of options, so an open class of queries. And it's easy to extend the data in a language model. So these are the motivations behind this idea. And so this paper is from Facebook research. And what they did in this paper is that, sorry, I don't need my laptop. My laptop might be famous, I'm sorry. And I turned it off. So yeah, so what they did is that they picked some knowledge source and also some language models, including BERT and almost some famous language models. And then with some considerations, including we're going to focus only on single tokens, not multi-token sentences. And also, what else was the consideration? Yeah, I forgot. Now I need my laptop. This was the actual joke, but I didn't mention in the beginning. Yeah, so yeah, they reduced the scope of the research mainly because to be able to compare the language models with knowledge bases. And I want to mention them because I found them really interesting. One of them is that when we talk about a knowledge base, the template that we use for retrieving information is fixed. And then if you choose another template instead of that specific template, the accuracy is 0. You can't retrieve any information. But with language models, there are many different templates that you can use, and the accuracy of the model depends on the template that you're using. So this paper, the accuracy that they report is actually a lower bound for the accuracy that they can obtain with a language model. Yeah, so they use rank-based metrics to compare knowledge bases with the language models. And single token. Oh, okay. Now I found the consideration. The other consideration that they only look for objects in a we have subject, relation, and object. So the queries that they run and compare the knowledge base with the language model is only about retrieving object, not the relation. And the subject can also be retrieved by changing the sentence. But the reason that they don't compare the language model with knowledge base in terms of retrieving the relation is because it's going to be really complex, and you can't really define whether the relations are exactly the same or not easily. So what they report is that BERT large is actually capable, compared to other language models and other supervised knowledge bases, BERT large performs better, and then its performance is actually comparable with knowledge bases in terms of retrieving factual information and relational data. That's it.
Okay, so thanks very much for everyone presenting and participating. So 2 things we want to do now is get some feedback from you guys on the session, and then also